Hello calculus fans, and welcome to section 2.7 where we talk about derivatives and rates of change. And this is kind of a big section, so go ahead and roll up your sleeves and let's get into this. The problem of finding the tangent line to a curve and the problem of finding the velocity of an object both involve finding the same type of limit. As we saw in section 2.1, this special type of limit is called the derivative. We're going to talk about derivatives a lot. And we will see that it can be interpreted as a rate of change in any of the natural or social sciences or engineering. So suppose we've got this curve here with the equation y equals f of x. We want the equation of the tangent line to the curve at the point P. So we've got this point P on the curve, and we want to find the equation of this tangent line here, this red line that's tangent to the curve. Well, if we want to find the equation of this line, we're going to need to know the slope of the line, but unfortunately, it's only touching at one point. So we can't use our formula for the slope of a line through 2 points because we just have 1 point. So what we're going to do is we're going to take this point P, which would be the point A, comma, f of A. That would be point P. And we're going to find another point. We're going to come over here to this point X and come up with this point Q. We're going to call this point Q. And point Q would be the point X and f of x. And then what we can do, we could find the equation of this secant line. Now, of course, that secant line, if we find the slope of this line, it's nowhere near the slope of the line that we want. So what we're going to do is slide this x over, which would cause Q to slide over here. And you can see as we get closer, if this is our point Q here, then the slope of our tangent line is better. It's closer to the slope of the secant line that we just made. This one is better at approximating the slope of the tangent line that we want, but it's still not very good. So we can slide x over even more, which slides this point Q over here. And so maybe this point Q here, then the slope of that secant line is pretty close to the slope of the tangent, but we will get closer and closer. So this point Q will slide all the way over here. And if we have point Q here, then we can use the slope formula, right? Because now we've got 2 points. So we know the slope of a line through those 2 points. Right here, the slope of the secant line PQ. Well, we're all set with that. The slope through PQ is just f of x minus f of a over x minus a. And all I'm doing is our formula we've seen lots of times, y2 minus y1 divided by x2 minus x1, right? So it's just the slope formula. Okay, so what we have here, this is the slope of the secant line. And what we're going to do is we're going to slide x along here, which slides q along here. We're going to take the limit of all these slopes of the secant lines. And the limit of those slopes of the secant lines is actually the slope of this tangent line. And that is what the definition says right here. The tangent line to the curve y equals f of x at the point P is a line through P with this slope right here. Notice we have this slope of the secant line, but we're taking the limit. We're taking the limit as x approaches a. So as x approaches a, gets closer and closer and closer to a, what is the limit of the slopes of these secant lines? And that limit is the slope of the tangent line. And just a little note here, sometimes when you work on the homework, it may say something about definition 1 from the book. So this is what our book calls definition 1. So it turns out there are 2 definitions that are very similar that we can use. This is the least popular. I wanted you to see it because it does come up, But there's another one. We're basically leading to a derivative formula. And this is a formula you can use for the derivative, but there's a more popular one that we'll look at in just a minute here. But first, let's find an equation of a tangent line to the curve at this point by using this. Because if you remember from the early in the class, when we had questions like this, the problem was always finding the slope to use here. But now we've got a formula for the slope. Whereas before, we would use the calculator to guess. We would make educated guesses by using the calculator to calculate a whole bunch of slopes using the slope formula for a line through any 2 points, and we would just pick points really close to the x value. But now we've got a new way to find the slope, and this will find the slope exactly without having to guess. So we're going to find an equation of a tangent line to this curve, but the key is it's just ultimately it's a line, right? It's an equation of a line, happens to be tangent. So when we're all done, we're going to have y equals mx plus b. Just like before, we need to find the m and the b. So now to find the m, we've got a formula right here. So we've got f of x, right? Here's our f of x. So instead of y equals the square root of 2x plus 1, we're going to say, okay, here's our function. F of x equals the square root of 2x plus 1. Here's x and y. So just remember this is a, and then 3 would be f of a. So it's sort of like the point a, f of a that is mentioned up here. Okay, so we've got this. So let's find this slope m, and we can use this formula to do it. So the formula says m equals the limit as x approaches a. A in our case is 4. And we've got f of x, which is 2x plus 1 under the radical, minus f of a. Okay, so here's a, and here's f of a. Now you could find f of a just by taking a, which is 4, and plugging it in here, right? If I plug a 4 in here, I'm going to get the square root of 8 plus 1, the square root of 9, which is 3. But you can also see there's a 3 is right here. So I'm just using this formula right here. So f of x, which is our function, minus f of a. Well, a is our x-coordinate, 4. So f of a, I just plug 4 into our function. So when we do that, we'll get 3. And we divide that by x minus a, which would be x minus 4. And then at this point, we've seen limits like this. So if I plug in a 4 here, I'm going to get what we have gotten a whole bunch of times before, 0 over 0. In section 2.3, we had a whole bunch of 0 over 0, and we had a technique for this. This one has a radical, so our kind of go-to technique for 0 over 0 with a radical is that we would multiply by the conjugate. Right, the conjugate over itself, so we're really multiplying by 1. And then we would say, okay, we're going to have to FOIL this, but because these are conjugates, the outside and inside cancel. So we just multiply first times first, last times last. The non-conjugate pair, we don't actually expand because we're going to get something to cancel. So this gives us a limit as x approaches 4 of 2x plus 1 minus 9, and down here we'll have x minus 4. So I'm going to write something and ask a question. Okay, here's my question. Is that okay? Of course not. I know what you're thinking. You can't even stand to look at it, right? We can't have this hanging out here. That's not the same thing. We need parentheses here, right? Remember, details. Details are always going to matter to us. And they will to you when you're out of college, done with college, making the big bucks, underworked, overpaid. People are going to expect you to pay attention to details. So 2x plus 1 minus 9, that's really 2x minus 8, right? That's really 2x minus 8. Just write this up here to save a little time. 2x minus 8. And then if we right now take the limit, I'm going to get 0 over 0 again. But can you see anything we can do here to get out of this 0 over 0? I think some of you are probably noticing we can factor a 2 out of there. So if we were to factor a 2 out of there, we would get limit as x approaches 4 2 times x minus 4, and down below we've got x minus 4 times 2x plus 1 plus 3. So we can cancel that, and that would give us the limit as x approaches 4 of 2 over 2x plus 1 under the radical plus 3. Okay, and I think we're out of trouble now. Now we can take the limit. I can plug in 4 here, and we'll get the square root of 9, which is 3 plus 3. So we get 2 over 3 plus 3, which is 6, which reduces to 1 over 3. So we've got our slope. So remember, we're looking for equation of a line. We know the slope now is 1/3. We have a point, so now we are all set. You could do this a couple of ways. Some of you probably learned using this equation right here, y minus y1 equals the slope times x minus x1. If you learned this technique, you just plug in your slope for m, and you use 4, 3 for x1, y1, x1, y1. They just plug everything and solve for y, and you will get your answer. The way that it's typically done now, what I think most people learn now, is to find b, and you basically start back off with y equals mx plus b. We take the slope, plug it in here for m, and then we pick we use the point that we have 4, 3, so that is x, that is y, and then you just solve this equation for b. So we would get 3 equals 1/3 times 4 plus b. So 3 equals 4/3 plus b. Now keep in mind that if I'm going to have to do something with this 4/3, I'm just going to think of 3. This is really 9/3. So I'm going to subtract 4/3 from both sides. So when I subtract 4/3, it's really 9/3 take away 4/3, which gives us 5/3 equals b. So then putting the pieces together, to answer the question, we get y equals 1/3 x plus 5/3. So that is the equation of the tangent line to this curve at the point 4, 3. And if you want to verify it, you could just graph on your graphing calculator. Put this function in, square root of 2x plus 1. Also put this one in there, and it should look like this is just tangent, just touching this curve at the point 4, 3. I mentioned earlier there were 2 ways to define a derivative. The way that we're going to do it next is the most popular way to do it. So sometimes we refer to the slope of a tangent line to a curve at a point as the slope of the curve at the point. So let's look at this next setup here. You get something very similar. We've got this curve y equals f of x. We've got this point P right here, which is the point A and f of A. And then what we're going to do is we're going to come over a little bit here. We're going to come over this distance h, and that will give us this point over here, which is going to be A plus h. So here's A, we go over h units to get A plus h. So then this point Q has an x coordinate, A plus h, y coordinate, f of A plus h. Once again, what we really want is we're going to have to find the slope of this tangent line to the curve. So we've got this tangent line we're looking for. And what we're going to have to do is start with the slope of this secant line here. And then what we're going to do, I mean, this is the same thing we did before, but the notation is different. The only difference is the notation. So last time we said this is A, this is X. And now we're just calling x a plus h. So instead of saying x approaches a, we're going to say h approaches 0. This gap here is going to approach 0. So as this h approaches 0, a plus h slides along here approaching a, and then this point Q slides along here. So the next point Q maybe is right here. So the slope of a secant line then is a little bit better. And of course, as Q slides closer and closer, the slope of the secant line gets a better approximation to the slope of the tangent line, which is the one we want. And then as it slides even closer and closer, we're going to end up looking for the limiting value. So at this point, that secant slope is pretty close, but we're going to do like we did before. The slope of the secant line looks like this. And we're going to once again just use the slope formula, y2 minus y1 over x2 minus x1. So that would give us f of a plus h minus f of a all over a plus h minus a, which of course cleans up to f of a plus h minus f of a all over h. And this is something you may have seen before. A lot of times in pre-calculus, you'll see something like this. Sometimes they'll call it the difference quotient. But we're going to use this right here. So we're going to do like we did before. This is the slope of the secant line. Secant, remember, cuts twice. All these blue lines are secant lines. We really want the slope of the tangent line, which is that red line that just touches, right? So much like before, we can take a limit. And this slope of the tangent line is really just the limit of the slopes of all the secant lines, right? Here's the slopes of the secant lines. We take the limit as h gets smaller and smaller and smaller, so the limit as h approaches 0, and we get this. And this is what, in the book, they call this equation 2. So in the homework, if they ever say use equation 2, they're talking about this one. So now let's try an example, just like we did last time. We want to find an equation of the tangent line to this hyperbola at the point 5, 1. Well, it's still an equation of a tangent line. In other words, an equation of a line. So you know it's going to look like y equals mx plus b. Now in example 1, we used the formula that we looked at before. Now we're going to look at our new formula. Now in truth, they both work. We could use the equation that we learned last time for the slope of the tangent line, what the book calls definition 1. We could use that with this problem. We get exactly the same we're going to get right here. So they're interchangeable. They're really the same formula, just a different numbering of the xy curve and the points that we're using, but it's really the same formula. But this is the most popular one, so this is the one I'll tend to concentrate on the most. So for this problem, if we're going to find an equation of a line, we need the same as before. We need to find the slope and the y-intercept, but this time we want to use this new formula for the slope, this new limit. So just remember, this is our function. So y equals 5 over x, we'll call this f of x equals 5 over x. So we need to find f of a plus h minus f of a. And again, a is going to be this 0.5. That's our a, right? And then this 1 is our f of a. Because if you plug in a, which is 5, into our function here, y equals 5 over 5, you get y equals 1. So we've got a, f of a. So we can just go ahead and say the slope is equal to the limit is h approaches 0, f of a plus h. Okay, so let me just write this out first. So f of a plus h is f of 5 plus h minus f of 5 all over h, because in this case, our a is equal to 5. Now I just want to review a little bit. So we have f of x for this problem is 5 over x. Right, this is f of x, 5 over x, right? So remember, if we want to find a value like f of 5, we just plug in 5 here. So if we have f of 5 plus h, remember wherever there's an x, we put 5 plus h. So just off to the side here, f of 5 plus h, wherever there's an x, we put a 5 plus h, right? So if this is f of x, this is f of 5 plus h, which is what we've got over here. So to fill in the rest of this, we're going to get this is equal to the limit as h approaches 0. F of 5 plus h is 5 over 5 plus h minus f of 5. Well, f of 5, I plug a 5 in here, I get 5 over 5, which is 1. It's going to be minus 1 all over h. So now, if we were going to take the limit at this point and plug in a 0, we're going to get 1 minus 1, which is 0 over 0. So we get 0 over 0. So what we're going to have to do to get out of the 0 over 0 is combine these two. So what I'm going to do is just turn 1 into 5 plus h over 5 plus h, because then it will have a common denominator, right? So if we do this, we could say, all right, this is equal to the limit as h approaches 0 of 5 over 5 plus h minus 5 plus h over 5 plus h all over h. Right? This is 1. This is equal to 1, but it has a common denominator. So now we can just keep that common denominator. So this is the limit as h approaches 0. We've got h over here, and now we've got a common denominator of 5 plus h. So I can put the numerators together, 5 minus this combination, right? So this negative is going to distribute through. So now the numerator is going to be 5 minus h, which cleans up a little bit. 5 minus h is just minus h over 5 plus h. And then if you look over here, instead of dividing by h, couldn't I instead multiply by the reciprocal of h? And h is just h over 1. So I clean this up. 5 minus h is just minus h over 5 plus h, which is here. But instead of dividing by h over 1, I'm going to multiply by the reciprocal. So I'm going to multiply by 1 over h. Right, and that's something we all learned in elementary school. If you have like 5/8 divided by 2/3, we never really divide, right? We instead turn that to multiply and take the reciprocal. So we would say this is equal to 5/8 times 3/2, and then we would do that math. All right, so that's kind of what we're going to do right here. So it's a little easier to see what's happening if we do this, because then we can see these h's are going to cancel. So h goes into here once, goes into here once, and that gives us a limit as h approaches 0 of negative 1 over 5 plus h. So we can finally take the limit as h goes to 0. The limit of that is going to be negative 1/5. Okay, so that is our slope. Kind of a lot of work, but that's our slope. And so then we can find b. So we need to find b now. We've got y, we've got m, we've got our slope. We just need to find the y-intercept. And again, there's that other way you can do this. Some of you learned this method, y minus y1 equals the slope times x minus x1. So if you learn that method, you can go ahead and plug in the slope, negative 1/5 here, and then x1, y1, plug those in and solve for y. Most of the time it's taught this way over here where you find b, so we just go back over to y equals mx plus b. We plug in negative 1/5 for the slope, and then we use the point that we've got, 5, 1. Plug 5 in for x, 1 in for y, and we would get 1 equals negative 1/5 times 5 plus b. So which means 1 equals -1 plus b. So if you add 1 to both sides, you get 2 equals b, which means the answer to our question is y equals -1/5 x plus 2. So that is the line, equation of the line tangent to this hyperbola at this point. And of course, if you want to check to see if it's reasonable, you could graph this and graph this in your graphing calculator, and it should look like this is just tangent to this hyperbola at the point 5, 1. All right, so far, just a quick summary, we found 2 equations using limits to find the slope of a tangent line. And now we're going to find a way to find instantaneous velocity. And it's going to sound very familiar. So remember from earlier in section 2.1, we said instantaneous velocity is the limiting value of average velocity over shorter and shorter time intervals. So suppose an object moves along a straight line according to an equation of motion, which is given here, where s is a displacement, which is the directed distance of the object from the origin at time t. Now you talk more about displacement in a physics class because you'll have vectors. In Calc 1 and Calc 2, typically all of our motion is going to be straight line motion because we don't have vectors. You'll have vectors in Calc 3, but usually in Calc 1 and Calc 2, our motion is just going to be straight line motion. So this function, s equals f of t, that describes this motion is called the position function of the object. We got a formula here that we've seen before for average velocity. We said average velocity was displacement over time. We had this formula here. The formula was the final position minus initial position divided by final time minus initial time. And really this is essentially just a slope formula on a position versus time curve. So if you take a look at the curve below, we've got a position s versus time curve. You've got our function here. So s is a function of time. And we've got the curve that goes like this. We've also got this point A and this point A plus h along the x-axis. That will give us this point P here and this point Q here. So very familiar story here, right? We're going to look for this. We want to find the instantaneous rate of change in position with respect to time right at point P, and that instantaneous rate of change would give us really is the slope of that tangent line right there. So what we could do once again is find the slope of the secant line through PQ, and then let this little distance here, this is A plus h, so once again this gap is h. We let h, this gap, approach 0. Q comes along the curve approaching P, and then the limiting value of the slopes of all these secant lines will be the slope of the tangent line right there, which is what we want. We can see this right here below. The average velocity is the slope through PQ. And average velocity, if we did just like what we did before, if we use the slope formula, we'll get y2 minus y1 over x2 minus x1. And just like before, a plus h minus a ends up with just h. So we keep using the slope formula. So even this up here is the slope formula. If we just label this differently, we'll get the same thing here. This is the slope formula, this is the slope formula. And they both will give us average velocity. See how this one here? This is average velocity right here. This is average velocity right here. Once again, we're using the two different variations of that same formula that we started with earlier. We had two variations of the formula for finding the slope, and now we have two variations for finding the average velocity. But once again, we're going to kind of focus on this variation here. So if we want to find the velocity, and when you see velocity without average, this is understood to be instantaneous velocity. So this is the instantaneous velocity. That's IN. Instantaneous velocity, velocity at time A, and now we're going to take the limit as h approaches 0. So again, this gap here is h. All right, this little gap. We're going to let this gap approach 0. So as h approaches 0, this comes over here, q comes over here, and then the velocity, which is the rate in position with respect to time, or the change in position with respect to the change in time, that instantaneous velocity is equal to the limit of all of these secant line slopes. And if you look, you'll see this formula looks very familiar. This is exactly the same as the slope of the tangent line formula. So velocity can be interpreted as the slope of a tangent line if you have the position versus time curve. And we'll see later that there's a lot of derivatives. Well, all derivatives can be interpreted as the slope of a tangent line, and the derivative just depends on whatever the vertical and horizontal axis are. In this case, position versus time, you find the slope of that tangent and you get the instantaneous velocity. And now I know what you're thinking. You're thinking, well, we've got a new formula. I sure would like to try it out. And that's what I knew you'd be thinking. So we've got something to try right here. So if you recall, we had Galileo's model for free fall, again with no air resistance, is this right here. This gives a distance fallen in meters, so this will give us a distance in meters after t seconds. So we plug in t, we get the distance fallen. So for example 3, suppose we drop a Doodlebop's action figure from a balloon 500 meters in the sky. What is his velocity after 3 seconds? Once again, ignoring air resistance. Now, I still remember when this came up because my son went through this little time period where he liked to watch the Doodlebops and the Wiggles. And if you're an adult, watching the Doodlebops and the Wiggles can be quite painful. So I'm sure there were shows that you watched that just were very difficult for your parents to take. And your kids will do the same to you. It just seems to be something that happens. Now, if you can't relate to this pain yet, you've got a microwave at home, imagine. Maybe put your head in there for about 30 seconds. And that will be about like watching Doodlebops or the Wiggles if you're not a child. Very difficult. So anyway, that's where this problem came from. And of course, don't try the microwave thing. I was just trying to explain how these shows are sometimes painful for adults and kids love them. So let's say we had a Doodlebop's action figure. We drop it from a balloon way up in the sky, and we want to find its velocity after 3 seconds. Now when we say velocity, we want the instantaneous velocity. Also, what we're going to do, we're going to find a general solution. So a general solution just means it's a solution for any time. So we'll say for time A. And then after we have it, we can plug in 3. Because then maybe we'll say, what about after 5 seconds? So we don't have to redo the whole thing again. We'll have a general solution, so then we could just plug in 5 seconds. Okay, so to do this, we can look at our brand new formula we've got for instantaneous velocity at any time A. We know that it is the limit as h approaches 0 of f of a plus h minus f of a all over h. And our formula right here, our function is this, 4.9t squared. So here's where sometimes students get really confused. So I'm gonna write some things down up here in practice. So if f of t is 4.9t squared, and I want to find f of a. Okay, we typically don't have any problems with this. Wherever there's a t, I'm going to plug it in a, right? So f of a, no problem, 4.9a squared. Now something about f of a plus h always throws us off, and it shouldn't. Just wherever there is a t, I'm going to plug in a. So if I put a plus h here, wherever there's a t, I put a plus h. And it just, for some reason, when there's two terms in here, it just gives us all kinds of trouble. It's the same thing though. F of a plus h means wherever there's a t, I'm going to write a plus h. So I'm going to have 4.9, not t squared, but a plus h squared, right? Just don't think about it too much. It should be easy. If it seems difficult, you're thinking too much. Think of it like this. What would f of Bob be? Just don't even think about it. Think of like something ridiculous like this. F of Bob, wherever I see a t, I'm going to write Bob. 4.9 Bob squared, right? Just think of it like that. These give us trouble for some reason with the two terms, so just don't think about it so much. Think of, what if it said Bob? Wherever there's a t, I'm going to write Bob. That should work. So over here, if we continue, we've got the limit as h approaches 0. F of a plus h is going to give us 4.9 a plus h squared, right? So that's this part. Then we have to go minus. Automatically put the minus there. And now put f of a, which is 4.9a squared, all over h. Then from here, whenever we do one of these problems, we just have to do some cleanup. And in a problem like this, we'll get some things to cancel. So I need to square this. Remember, don't just write a squared plus h squared, right? That's not going to work. This is this binomial squared. It's like the FOIL method, right? It's like take two of these a plus h's, line them up and multiply them together. So this thing is really a plus h times a plus h, right? We have to think of like the FOIL method here, right? First, outside, inside, last, or first, outer, inner, last. So you go first times first, a times a is a squared, outside times outside is a times h, inside times inside is another a times h, gives us 2 a times h, and then last times last is h squared. So when we fill all this in, we get the limit as h approaches 0, 4.9 times a squared plus 2ah plus h squared minus 4.9a squared all over h. And then we can distribute this through here. So that will give us the limit. Remember, we need these limits as h approaches 0. And also, I probably should have mentioned, like, we can't really take the limit right now, because if we plug in a 0 for h, we're just going to end up getting 0 over 0. That's kind of what you probably expected. So then we get, once I distribute 4.9a squared plus 9.8 ah plus 4.9h squared minus 4.9a squared all over h. Okay, so we can see this is going to cancel. And then we will have the limit as h approaches 0, 9.8 ah plus 4.9h squared all over h. And you can see there are three terms here. All of them have a factor of h, so we can cancel an h out of all of them. H goes into there one time. This becomes just h. So we end up with the limit as h approaches 0 of, let's see, 9.8a plus 4.9h. And now we can actually take the limit. H goes to 0, and we are left with 9.8a. So Our velocity at any time A is 9.8 a. So now if we want to know what is the velocity after 3 seconds, we can just plug 3 in, right? So the velocity after 3 seconds is 9.8 times 3, which gives us 29.4. And looking at the units we're using, it would be meters per second. And I'm going to give you a fast approximation that I use sometimes. So if you're not as familiar with the metric system, which if you're born in the United States, you probably are not. Although everywhere else in the world, pretty much, I think there's a couple exceptions, maybe like Burma and I think Liberia. And I think that's it, and us, who don't use a metric system. So sometimes in technical classes, you'll be using it. So you get something like 29.4 meters per second, and we're lacking the intuition because it's not something we're used to. So we're used to like miles per hour. So there's a real fast conversion you can use. It's just the square root of 5. So if you have meters per second and you multiply by the square root of 5, you'll get approximately miles per hour. Usually accurate to within a couple of decimal places. So it's pretty good without having to go through a whole unit conversion. Just if you've got meters per second and you want miles per hour, just to get a ballpark approximation that's actually fairly accurate, just take your meters per second and multiply it by the square root of 5, and it'll be pretty decent and easy and fast conversion. Okay, and finally we get to the last part here. How fast is this action figure traveling when it hits the ground? Well, we know it's going to hit the ground when it has traveled 500 feet, right? Because this action figure was dropped from a balloon 500 meters in the sky. And we've got a function here, f of t equals 4.9 t squared. And remember, we are told that this is going to give the distance fallen after t seconds. This is the distance fallen after t seconds. So it's going to hit the ground once it has fallen 500 feet. So I'm going to let this be 500, right? It hits the ground when this is equal to 500, because this is the distance fallen in meters after t seconds. So I can set that equal to 500. From here, just divide each side by 4.9, right? And that'll give us t squared equals 500 over 4.9. Of course, we want t, so we just take the square root of both sides. And we get t equals roughly, I'll say 10.1 seconds. Once again, remind you, in calculus, we don't cover significant digits or significant figures. So you'll cover that in calculus, you'll cover that in probably in physics and chemistry. We just don't cover it in this course. So for something like this, I'm just going to say t equals 10.1 seconds. Depending where you're around here, you'll get little variations. It's not going to matter to us. You'll clear all that up. You're going to learn someday in physics, when you talk about significant digits, you're going to learn that 2 times 6 is only 10. Very surprising. But for us, we're going to still call 2 times 6 12, because we're not going to be too worried about significant digits at this point. So we know that it's going to take just over 10 seconds to land, so we can find the velocity then. We can find the velocity at that point. Velocity at this time is v at 10.1, which is equal to 9.8 times 10.1, which is roughly 99 meters per second. Pretty fast. If you do that quick conversion and multiply 99 times the square root of 5, you'll find out that thing is traveling right around 220 miles per hour or so, 221 miles per hour. Pretty fast. So now we're coming up on derivatives, which is kind of one of the main concepts in calculus. We have seen that the same type of limit arises in finding the slope of a tangent line or the velocity of an object. We can see these are the same limits right here for the slope and the velocity. This type of limit arises whenever we calculate a rate of change. In math, business, any of the sciences, or engineering, the derivative is an instantaneous rate of change. And we've got a definition here for the derivative of a function f of x at a number a. And look at the notation here denoted by f prime of a. Is this f prime of a is the limit as h approaches 0 of f of a plus h minus f of a all over h, provided this limit exists. Now this is actually equivalent to another formula which we've looked at. I told you it's not as popular, but it's equivalent to this. The limit as x approaches a, f of x minus f of a over x minus a. We didn't really do too much with this one, but just so you're aware, these are the same thing. And I'm also going to talk about the notation you'll see. So notation for derivatives, there are a lot of them. So I'm just going to put some here that you'll see. So we'll see f prime of x. We'll see dy dx. All these mean derivatives. And these will come out a lot more in the next section 2.8 also. Sometimes you'll see df dx. Y prime, you'll definitely see a lot. Sometimes in physics applications, you'll see this y with a dot. I think it was Newton who used to use that. The most popular ones you'll see are like f prime of x, dy dx, y prime. A couple more that you may see occasionally is something like this d with a subscript x of f, means the same thing. Sometimes you'll see like this notation and then a function maybe in parentheses like this. So this is like saying d dx, meaning the derivative of this function, f of x. d dx, and then in parentheses, f of x. So all of these things mean the same thing. They mean the derivative. But now that we've got our official formula here, we can try this one out. This says find f prime of a if f of x equals x squared minus 3x plus 5. So we can try out this formula here. Again, sometimes we get into trouble with this f of a plus h, but f of a plus h just means wherever there's an x here and here, I'm going to write a plus h. All right, so let's try one. Our first derivative. Here's the formula. And we've got f of x right here. F of x is given right here. So we just need to plug in what the formula says, f of a plus h. So I'm going to put a plus h here, and then minus f of a. Well, f of a is just this thing with x's replaced by a's. So what you should do is try this out, this first step. Just pause the video a second and write down what goes here. And then check back and see what you got. Okay, so hopefully you tried it. And you're not just waiting for me, right? The only way to learn this stuff is to actually do it. So if you didn't try it, go ahead and try it. Okay, so f of a plus h. So what I'm going to do, this is f of x right here, right? Just let me make this really clear. Here's f of x. So f of a plus h means I'm going to put a plus h here and here. So this is going to be the limit as h approaches 0 of a plus h squared minus 3a plus h plus 5. Right? This is f of a plus h right here, f of a plus h. Then let's go minus, so let's go minus f of a. Well, I'm going to do something wrong here and see if you guys can figure out what thing would happen if I did it like this. I've got this divided by h. This is easy to do, but there's a mistake here. So I have to go subtract. I have to subtract f of a. Well, f of a is going to be 3 terms, so I'm going to need parentheses, right? I need this. Because now I've got f of a plus h minus f of a. So then what we've got to do, we have to square this. We have to distribute the -3 through and distribute this negative through. And then algebraically clean up the mess. So this is equal to the limit as h approaches 0. So that a plus h squared would be a squared plus 2ah plus h squared minus 3a minus 3h. Because what I'm doing here, I'm just distributing this through. Then I get plus 5. And then distribute the negative, you get minus a squared plus 3a minus 5 all over h. When we do this, any term that does not have an h should cancel, because we need to have all h's left so that we can divide everything by an h to get out of the 0 over 0. Because these are all going to be 0 over 0. So if you try to take the limits, at any point you're going to get 0 over 0 until we clean stuff up. So you've got a squared minus a squared. We have got minus 3a plus 3a. We've got plus 5 minus 5. So I'm just going to kind of group those together. A squared minus a squared. They will go. Let's see, minus 3a plus 3a. Those will go. Plus 5 minus 5. That goes. Look at everything that's left. Everything that's left has a factor of h, right? There's a factor of h with everything. So this gives us the limit as h approaches 0, 2ah plus h squared minus 3h all over h. And now, although we're still in 0 over 0, if I plug in a 0 here for h, I'm going to get 0 plus 0 minus 0, which is 0 all over 0. But you can see that every term has an h. So I'm going to cancel out these h's. This becomes h to the 1. That just goes to 1. That goes to 1. So then we end up with the limit as h approaches 0 of 2a plus h minus 3. And now we can take the limit, allow h to approach 0, and we'll be left with 2a minus 3. Now what's significant about this is that this formula, this right here, this is the formula for the slope of the curve, the slope of this curve at any x-coordinate. So if I want to know the slope of this parabola when x is 2, the slope of the tangent line to this curve when x is 2, I just plug in a 2 here, and I would get 2 times 2 minus 3, which is 1. Okay, so that formula, this formula right here, it works for any x-coordinate. If you want to know for this parabola, now we know this parabola, we know what they look like, right? It's a positive coefficient, so it's going to be a smiley face, right? The curve opening up. Well, the formula for the slope of this curve at any x-coordinate is right here. So you just plug this in and it'll give you the slope of the curve along here. And what this is telling us is that if we were to graph this, you could put this on your graphing calculator and look at the point 5 when x is 5. If you go and look at the curve here where x is 5, the slope of the tangent to that curve is 7. And if you look over here where x is -1 and look along this curve where x is -1, the slope of that tangent is -5. So when we find the derivative, we're coming up with a formula for the slope of the curve at any x-coordinate, which is like saying the slope of the tangent to the curve at any x-coordinate. Let's put some of these ideas together here. So we can say the tangent line the tangent line to y equals f of x at a f of a, right? This would be the point A, f of a, because here's y equals f of x, is a line through a f of a whose slope is equal to f prime of a, which is the derivative of f of x at x equals a. So the slope of the tangent line is equal to f prime of a, which is the derivative of the function at x equals a. So there's a whole bunch of ways you can discuss this. You can say f prime of a. So f prime of a, here is the function. So here's f of a. F prime of a is the derivative of the curve at a, which the derivative of the curve at this point is equal to the slope of the tangent at that point. So we could say that this is equal to the limit as h approaches 0 of f of a plus h minus f of a all over h. We could also say this is equal to the slope of the tangent line at P. We could also say this is equal to the slope of the curve at P. Like the slope of the curve y equals f of x at P. So sometimes people mention the slope of the curve, sometimes they talk about the slope of the tangent line, but they're talking about the same thing. And also it's equal to the derivative. Derivative means rate of change. The derivative of f of x at x equals a. All of these mean the same thing. And now using those ideas above, we're asked to find an equation of the tangent line to this parabola at the point 2, 3. Well, this parabola was from the previous page. We worked with this parabola on the previous page and we found the derivative. We found that the derivative of that at any point a, f prime of a, is equal to 2a minus 3. So since this gives us a slope formula, once we have this, we don't need to guess. We don't need to use a table of values. We can actually come up with what the limit is. So we can just use f prime of a is equal to 2a minus 3. This would be a and f of a. So we plug in a 2. 2 would be the a. So f prime of 2 is going to be 2 times 2 minus 3, which is equal to 1. So we've got the slope. So if we want to find the equation of a tangent line to this parabola at the point 2, 3, we know the slope is 1. Plug in a 1 for the slope. And I'll take 2 and 3, plug in 2 for x, 3 for y, and then we can find b. So 3 equals 1 times 2, which is 2 plus b. So if we subtract 2, we get 1 equals b. So we end up with y equals 1x, or just x plus 1. So that is saying that this is the equation of a tangent line to this parabola at the point 2, 3. So once again, if you punch this in your graphing calculator, like for y1, plug this in for y2, it should show that this is tangent to the parabola at this point. Okay, then we have got example 6, which says a particle moves along a straight line with equation of motion, which is given here. So remember, we're going to have particles always move along straight lines for us. So it'll be something like we've got this line going here, and we've just called this our position S. And this is just going to tell us the position. So it's important to know this is not the path of the particle, right? This is not some running down. The path is, the particle is not following some path of some particle opening down. This just tells the position of the particle. So when time is 0, the position is 80. So this is 80 over here, and it's measured in meters. So if we have some origin, let's say this is the origin here. Let's say this is at location 0. when time is 0, we're at 80 meters. So we'd be out here somewhere at 80 meters. So remember, this is not the path of the particle. It just tells where the particle is. And also in Calc 1 and Calc 2, we typically have motion left and right or up and down. Now, there's some, in Calc 2 you make some exceptions. If you look at parametric equations or polar equations, then you can have particles that move all over the place. But for the most part, without vectors, we're going to have straight line motion. All right, so S is measured in meters, T is in seconds, and they want us to find the velocity and the speed when T equals 6. And then a little note here, just to recap what I just said. The object moves in a straight line. F of T is the position of the particle, not the path of the particle. Also, a lot of times in calculus you study these so-called particles. Well, it's not that you're going to be studying particles, but a lot of times the center of mass of a large object could be treated like a particle. So that's why you'll see this a lot of times. So this particle, it could be the center of mass of a satellite. So it isn't necessarily just a particle, but we can treat it like that. But before we start this one, I want to go over something, make sure we're good on this idea. So let's say we've got this function, this position function of time, and we're going to call this position. Okay, this is our position function. And if we're using the metric system, often this will be in meters. And then what we do is we take a derivative with respect to time. And that gives us velocity. And velocity is the derivative of the position function. So we take the rate of change of position with respect to time, we get velocity, and then oftentimes that's measured in meters per second. Okay, so then we'd have velocity, and then if we once again take the derivative of velocity, this time with respect to time, then we get acceleration. So acceleration is equal to the derivative of velocity, and it's equal to the second derivative of position. And that is acceleration. And that is in meters per second squared. Now really what it is meters per second. But instead of dividing by seconds, you could think of multiplying by the reciprocal of seconds. So that'd be like meters per second times 1 over seconds. And then that would give us meters per second squared. So we usually just write meters per second squared because it's a little less awkward than meters per second. And then there's some applications, not too many, but you can actually take a derivative of acceleration. So if I take the derivative one more time with respect to time, derivative of acceleration with respect to time, you get what's called a jerk. So like if acceleration changes quickly, the car that you're in will jerk, right? So it's not actually a bad name, but we don't really do too much with this. But we will see all kinds of these in Calc 1 and Calc 2 and actually Calc 3 also. You'll see it in physics classes. So we'll see this a lot. So this is how it goes. You start with position, you take the derivative with respect to time to get velocity. Take the derivative with respect to time and you get acceleration. So let's take a look at this problem. They want us to find the velocity and the speed when t equals 6. So what we can do, we can just find the velocity when at a, and then we can plug in any number we want, 6, 5, 4, whatever we want. So the velocity at time a is equal to the derivative of position. So it's equal to f prime of a. And then we can use our derivative formula above, which says that the derivative is equal to, or even we could use the velocity formula because they're the same formula, remember. It's the limit as h approaches 0 of f of a plus h minus f of a all over h. So in this case, we've got the limit as h approaches 0 of f of a plus h. Well, remember, this is our function f of t. So if I want f of a plus h, I need to put an a plus h here and an a plus h here. So that would give me negative 5.2 a plus h squared plus 50 a plus h plus 80. All right, so this is f of a plus h. Then I have to go minus f of a. Well, f of a is just like f of t, but I'm going to put an a in the place of the t. Okay, so that one's a little easier. Just remember I need a parenthesis here. So I go minus 5.2 a squared plus 50a plus 80 all over h. Now we've done enough of these where you'll probably get the idea that once we expand all of this, we're going to get a lot of things to cancel if we've done everything correctly. So let's go ahead. You should actually stop the tape and try this one because this gives us some trouble sometimes getting through the algebra here. So you probably want to try this one. Just expand everything, cancel everything, see if you can get rid of the 0 over 0, and then check back. All right, so hopefully you checked back, and hopefully you got something like this. So this is going to be equal to, the limit is h approaches 0, of negative 5.2. And if I expand the a plus h squared, I get a squared plus 2ah plus h squared. If I distribute the 50 through, I get plus 50a plus 50h plus 80. And now I'm going to take this negative and distribute it through, so basically all the signs in the parentheses will change. So we get plus 5.2a squared minus 50a minus 80 all over h. I just got one more thing to do just to expand. I'll just distribute the negative 5.2 through, and then we should be able to just clean up a lot of things. So it's the limit as h approaches 0. Negative 5.2 a squared minus 10.4 ah minus 5.2 h squared. Then all the rest of this will just come along just as it is. Okay, it's kind of a long one. And then over h, and now look for things to cancel. So let's see, we've got negative 5.2 a squared, 5.2 a squared. We've got plus 50a minus 50a. And we've got plus 80 minus 80. Okay, and I think everything else has an h, which is good, right? That's what we want, because then we can finally cancel that h out. So we've got negative 10.4 ah minus 5.2 h squared plus 50h all over h. And now we've got 1, 2, 3, 4 terms. They all have a factor of h, so we can cancel that h out. So that goes, that becomes h to the 1, that goes, that goes. And finally we get equals the limit as h approaches 0 of negative 10.4a minus 5.2h plus 50. Finally, we can take the limit. This term goes to 0. So we take the limit. There's no more limit there. We get negative 10.4a plus 50. So this gives us the velocity at any time a. So if they want the velocity when time equals 6, we just have to plug a 6 in there for a. Okay, so what we have got is velocity at time a is negative 10.4 a plus 50. So velocity at time 6, at 6 seconds, is negative 10.4 times 6 plus 50. And if you do the math here, you get negative 12.4. And the units are going to be meters per second. And then the question is, what is the significance of this negative? So, although we don't have vectors, we do have a direction. So when we have left-right motion, if we're going to the left or right, straight in a line, of course, left or the right, typically, this is arbitrary, but typically we say motion to the right is positive, motion to the left is negative. So the significance of the negative just means that we are moving backward, right? So, or to the left. So normally we consider motion to the right to be positive. So a negative velocity just means we're moving backward. Likewise, if we have up or down motion, we have motion up or down, positive, or up is considered positive, typically, down is considered negative. So the significance of the negative just means that we are moving backward. Now that's velocity. Velocity can be positive or negative. You'll see in physics or in Calc 3, you'll see that velocity is actually a vector concept. So it has a magnitude and it also has a direction, and the negative gives us the direction. But speed is different. I'm going to make a little note here. Okay, speed is said to be a scalar quantity. It just has a magnitude, no direction. Speed is the absolute value of velocity. So there's no negative with speed, just like on your car. There's no speedometer that has a negative. Even when you go backward, it doesn't give you a negative. So the speed at 6 seconds is just equal to the absolute value of 12.4, which gives us just positive 12.4 meters per second. Okay, so speed is always going to be positive. Okay, we are close here. This is the longest video I've ever made. I'm sure you guys are going to be shocked because I'm sure time just flies by when you're listening to these videos. But believe it or not, this has been over an hour and 12 minutes. So the last thing we have to look at is econ applications. One thing you need to know about applications in economics when we have mathematical models, they are not meant to be precise like a physics model. A physics model, you can control these. You learn a lot about laws of physics because you can control all the variables. Not so in econ. So mathematical models in econ have to be good enough to give us some information, but we don't expect the precision. So if I hold up a pen and drop it, we can make all kinds of predictions about how long that pen will take to hit the ground, how fast it will be traveling when it hits the ground, and they're going to be very accurate. And all physicists or mathematicians will get pretty much the same answer. But with the econ, it's just not like that. We can't control the experiments. You can't say go into a country, take all the money away, and try experiments to see how wealth accumulates, right? So econ is just one of those areas where the models are useful, but they are not precise. So you'll notice if you go higher up in econ, a lot of polynomials. The models are really nice. They're easy to work with. A lot of them are polynomial models. You'll see later, they all have derivatives. They have, when you learn Calc 2 about integration, polynomials are great for integration. So they look a little different than some of you see in engineering. But with that in mind, let's take a look at this cost function. I'm going to draw a typical cost function. Oftentimes cost functions look something like this, where there's an increase, slow and steady increase, and then maybe at some point it shoots up. So this point right here, so we've got quantity and cost. This point right here, often in econ you call this the fixed cost. So even when nothing is produced, the quantity is zero, you still have these fixed costs. So you still have to pay rent on the building, for instance, or electricity, even if you're not making anything. And then as the quantity increases, the cost, of course, increase. It takes material to make the products, it takes labor to make the products, and then sometimes with the typical cost function, it'll shoot up here. So maybe at this point, it could rise because maybe you need additional shifts or overtime or more equipment or something like that. So this is just, let's say this is our y equals c of q, where q is the quantity produced that we're producing, and c is the cost. The derivative of the cost function gives a rate of change. Which you would expect, right? It's the derivative, it's the rate of change, and it's called marginal cost. So when you're in econ and you hear the word marginal, just think derivative. There's marginal cost, there's marginal profit, there's marginal revenue. Marginal cost, in our case, looks like this, C prime of Q, right? So cost is C of Q, marginal cost, or the derivative of cost, or cost prime is C prime of Q. It is the change in cost over the change in quantity. So if you look at the units, we can see the units, dC, dQ, change in cost over change in quantity. This is dollars, right? The cost is in dollars. The quantity would be in terms of units. So C prime of Q is measured in dollars per unit. And marginal cost gives a change in the cost function, and the quantity, which is the independent variable, is increased by 1 unit. Now you may notice something here. We're increasing this by 1 unit, so it doesn't really sound like what we've been talking about, instantaneous rate of change. So we're sort of assuming this is going to hold for that 1 unit, which we'll talk about in a second here. But before we do that, let's just talk about marginal cost. It can be described in various ways. So marginal cost, remember when you hear marginal, just think derivative of the cost function. So we can think of it as the rate of change, because it's a derivative, of the cost function with respect to the number of items produced. Or we could think of it as the slope of the cost function curve. So sometimes if you take an econ class that doesn't have calculus, you'll look at the cost function curve and you'll find the slope of a tangent. So we would, in calculus, of course, just take the derivative, but it is also the slope of the cost function curve. And for us, most importantly, this will be the description that's most useful for us. It's the cost to produce an additional item. Because it's the rate of change of the cost function at a particular point, and we're talking about increasing by 1 unit, so that would give us the actual cost to produce an additional item. And then here's the note that I had mentioned earlier about a little bit of a problem with what we're doing. So we are using a continuous function, right? Calculus is continuous math. So we're using a continuous function to describe a discrete process. Because really, if you think about a graph here, if this is quantity of products, really, this is going like this, right? We have like 1, 2, 3, 4, 5. These are discrete numbers. It doesn't make any sense to talk about 1.275. So when we do this, we're saying the marginal cost, or the derivative of cost. Now we know the derivative is equal to the instantaneous rate of change of cost with respect to the rate of change of quantity, right? dC dQ. Well, it's approximately equal to delta C over delta Q. Remember, delta just means like a change where when we take a derivative or a limit has been used, then we put the d, like typically we'd have like dy dx. So it's approximately the same. So we're holding this to 1 unit, right? The change in quantity would be 1, so that we really have the change in cost. So the marginal cost is approximately equal to the change in cost. But remember, econ models are not meant to be precise. They're meant to be good enough to give us good information so we can make good decisions, but nobody expects them to be precise. So because of that, even though these are not exactly the same, oftentimes it's just quicker to find this, so we'll just take the derivative, and that's what economists do all the time. So they will take the derivative even though we are really using a continuous function to describe a discrete process. So really, this cost function wouldn't be smooth, it'd be clunky, right? It would jump up and like it'd be a step function over here, but we're gonna approximate it with a smooth curve. And these cost functions will be discussed in more detail in other sections here. But basically, we're going to do this. We're going to talk about both of these. We'll talk about marginal cost. We'll talk about also the change in cost. So to see the kind of things we need, we've got example 7, which says the cost of producing X ounces of Skull Crusher energy drink is C equals F of X dollars. Using units, explain the following. So you just want to explain, like, what is this telling us in the context of this problem, right? They're giving us a cost function. And so X is the ounces of Skull Crusher energy drink. And this was from years ago, a student of mine, I believe, was selling this, and I think it was called Skull Crusher energy drink. And it was like real high energy, like a 5-hour energy, but lots of caffeine. And I think later some other students of mine said that they were outlawed or something like that. Like there's just too much stuff in those. So anyway, that's where this comes from. So if we explain this, what it's saying is 200, that's our input ounces, and the output 350 is the cost. So what this is really saying is, and this isn't really calculus, this is just a regular function notation. This says it costs $350 to produce 200 ounces of Skull Crusher. Right? Just the cost function. This is just the cost function, input 200, output 350. So this means for 200 ounces, the cost is $350. Now this is the new part. This is something this is calculus, right? Because this is the rate of change of the cost function at this point. So basically this is saying we've made 200 ounces of Skull Crusher, and at this point the cost is changing by $1.40 per ounce. Right, so we're taking a derivative, but we're assuming it holds steady for 1 unit, right? So we're holding steady for 1 unit. So what this says, we could say, I'm going to say this a couple of ways. First, I'm going to say, after producing 200 ounces of Skull Crusher, the rate of change of the cost function is $1.40 per ounce. All right, so that's one way you could interpret this. The rate of change is $1.40 per ounce. Or what's probably more useful is just think of it like this. We have made 200 ounces of Skull Crusher. If we make 1 more ounce, it's going to cost $1.40 because the rate of change at that point is changing by $1.40 per ounce. So an easier way to say this, and maybe a more useful if you are making a business decision, you could say the 201st ounce will cost approximately $1.40 to produce. Now technically this holds going the other direction also, so you could say the 200th ounce also, right? Because it goes, we're assuming these hold steady for 1 unit, and I wrote the approximately here because really we're thinking of an instantaneous rate of change holding steady for 1 unit. So basically it means we have made 200 ounces, and at that point the cost function is changing by $1.40 an ounce, which means if I make one more of these, it's going to cost about $1.40. Okay, so either of these are okay. Hopefully they make sense. Then we've got a little note here. It says the average cost of producing the first 200 ounces is $1.75 per ounce. Now where this came from is I took the $350 that it said to produce 200 ounces. I divided that by 200 ounces, and that's where I got the average cost of $1.75 per ounce. But the cost of producing the 201st ounce, it says the cost of producing the 201st ounce is less than the average cost per ounce of producing the first 200 ounces, because we just found out the cost of producing that was $1.40 per ounce. And this is typical because of economies of scale. In econ, you learn about that. You basically, just the more products you produce, it generally is cheaper, per unit. A lot of the costs come with the startup. When you first start up, there's a lot of cost incorporated right there. Okay, so it was basically more efficient uses of fixed costs of production as output increases, is what you'll say. But that's for a later class in econ. Then there's one more note I need to make here, and that note is in some of the homework you may see something about average rate of change. There's a formula that you see sometimes in maybe a pre-calc class or an algebra class. Average rate of change, you can just use f of b minus f of a over b minus a. This is really just the slope formula again, but sometimes they'll call it average rate of change. And of course, if you hear the word instantaneous rate of change, that's a limit or a derivative, right? This is an average. There's no limit here. There's no derivative. Instantaneous rate of change, that's c. If it's a cost function, that's going to be like c prime. There's a derivative for instantaneous. All right. I hope you have been able to survive this longest video I've ever made. And try the homework. You should be good. I think we have covered just about everything you're going to see in this section. It's an important section, though. We're starting to talk about derivatives, getting into some of the good stuff. So give it a shot, and you know what to do if you have any questions. Make sure to ask me, and I will talk to you soon.